Namaskar. So, in the last class we were discussing about the step response of series RLC circuit and the parallel RLC circuits, and we saw that when we solve these type of circuits we get second order differential equation as a equation to solve. Sometimes these type of equations are difficult to solve when the circuit is more complex. So, we will try to understand another technique, that is called Laplace transform, which is easier to understand, and when we apply the Laplace transform in these type of circuits, it is more easier to solve the first order and second order circuits. So, before going into the details, let us first try to understand what is Laplace transform. So, in this module we will be introduced with the Laplace transform, and this is very powerful tool for analyzing the circuit with sinusoidal or maybe non-sinusoidal input. Now, Laplace transform is used to transform the circuit from the time domain to the frequency domain and obtain the solution. So, when you use the Laplace transform, you will first convert the circuit from time domain to frequency domain, obtain its solution, and then you will apply again the inverse Laplace transform, and the result will be transformed back in the time domain. Now, Laplace transform can be applied to a wider variety of inputs than the phasor analysis. So, in the initial lectures we discussed what is phasor and how we will solve the circuit with the help of phasor analysis. But phasor analysis has its own limitation, because it cannot be applied for very wide variety of inputs. So, that is why the Laplace transform is more easier and more powerful than the phasor analysis in solving these type of circuits. So, it provides an easy way to solve the circuit problems involving initial conditions, because it allows us to work with algebraic equations instead of differential equations. So, when we were discussing the RLC circuits, we saw that there were differential equations we compiled, and we were trying to solve those differential equations. So, differential equation solution becomes little bit complex, while when we compare with the algebraic equations, the algebraic equations are more easier to solve. So, the advantage of having the Laplace transform is that the differential equations which are coming in the circuits can be easily converted into the algebraic equations, and we can solve it easily. So, Laplace transform is capable of providing us a total response of the circuit, which comprising of both the natural as well as forced response, and that comes in one single operation. Now, how we will define the Laplace transform? Laplace transform is denoted by Fs, or you can say Laplace of Ft, and is given by the Fs is nothing but the integration between 0 minus to infinity Ft e to the power minus St dt. What is S? S is a complex variable and is given by sigma plus j omega. Now, since the argument St of the exponent should be dimensionless, that means that if you see St, one t is the time domain, so S would be the dimension of frequency, so that the combination St can become dimensionless. So, S will have a unit of inverse of second. Now, in equation 1 which you just saw, that is the definition of your Laplace transform, the limit which is minus 0 which is 0 minus indicates that we are talking about the time just before t is equal to 0. So, this makes sure that we are incorporating the phenomena like switching on and switching off the circuit. That means that the singularity functions like step response or impulse response are incorporated in this particular definition. So, this will accommodate the functions such as singularity functions which may be discontinuous at time t is equal to 0. So, what we can say about the Laplace transform? We can say that Laplace transform is nothing but an integral transformation of a function f t from the time domain into the complex frequency domain, and it is given by f s. Now, if you assume that in equation 1, if you assume that in equation 1 f t is ignored for time t less than 0, that means what you are doing, you are representing this mathematically as a function multiplied by the unit step function. So, what you can write f t you can club with the unit step function. So, you can simply write f t u t, or you can say f t for time t greater than or equal to 0. Now, what we saw in this equation, the integration starts from 0 minus to infinity. So, that means that it is one sided, that is unilateral Laplace transform. Now, if you want both side, that is bilateral transform, means you have to integrate f s from minus infinity to plus infinity. So, in that case your f s would be integration between minus infinity to infinity for f t e to the power minus s t d t. Now, the function f t some may not have a Laplace transform at all points. So, in order for f t to have a Laplace transform, the integration, the integral what we saw here should be having a finite value or it will converge. Now, if you see the expression, that is f s integration between 0 minus to infinity f t e to the power minus s t d t, if you put the value of s in this, so this will become the value, that is minus 0 minus to infinity integration e to the power minus sigma t f t into e to the power j omega t. So, now if you see the value, that is mod of e to the power j omega t is 1. How? Because this is Euler identity. So, you can simply write e to the power j omega t is nothing but cos omega t plus j sin omega t. So, if you take the mod of this will become root of cos square omega t plus sin square omega t. Now, the value of this is 1. So, what you can say, the mod of e to the power j omega t is equal to 1 for any value of t. So, it means that this is anyway is a finite value. So, you can take it out. The left part of the expression is the integration between 0 minus to infinity e to the power minus sigma t f t dt, and the integration should be finite. So, that means the value of this expression should be less than infinity, and this would be applicable for a real value sigma. Let us assume that value of sigma is sigma c. So, with this you can find out the value of the region of convergence for Laplace transform. So, you can say that real component of S, that is sigma, should be greater than sigma c for solution to converge. So, if you see the particular condition in the complex plane, So, sigma is varying in at the x axis and j omega is at the y axis. So, sigma c is your condition which is the boundary line. So, your solution of this particular expression to converge, your sigma should be more than the critical value, that is sigma c. So, right side of sigma c, if you have the solution, then you will say that your Laplace transform will exist. For left side condition, the solution will not converge. So, you will say that your Laplace transform will not exist. So, what we can say that mod of f s, if it is less than infinity, it means that the solution exists, and for rest of the section, the outside the region, the solution will not converge, and therefore, the Laplace transform will not exist in that particular region. Now, next is you need to find out the inverse Laplace transform, and inverse Laplace transform is given by Laplace inverse of f s, that is f t, and it is given by the expression that is 1 upon 2 pi j integration between sigma 1 minus j infinity to sigma 1 plus j infinity f s e to the power s t ds. So, this would be the expression for finding out the inverse Laplace transform, where integration is performed along a straight line. So, that is sigma 1 plus j omega, and where omega ranges between minus infinity to plus infinity. So, you will see that again the integration for any sigma 1 will be carried out along this particular line. So, what we can say, the function f t and f s are regarded as the Laplace transform pair, where f t and f s are the Laplace transform pairs. So, that means that there is one to one correspondence between f t and f s. Now, let us take few of the examples so that you can understand the concept. So, first is let us say unit step function. So, that is u t. Now, what we have to do? We have to find out the value of the Laplace transform of unit step function. So, if you see this is the unit step function. The value of unit step function is 1 at time t greater than 0, and it is 0 for time t less than 0. So, when you are asked to find the Laplace transform, you will use the expression for conversion of Laplace transform, that is Laplace of u t is nothing but integration between 0 minus to infinity 1 into e to the power minus s t dt. Now, this value is 1 for 0 plus. So, you can simply change the limits. So, it will become 0 to infinity now, and you will only have the component to integrate is e to the power minus s t dt. So, when you integrate, you will get minus 1 by s e to the power minus s t, and limit ranges between 0 to infinity. So, when you put the limit, you will get the value of Laplace transform equal to 1 by s. So, for the unit step function, the value of Laplace transform is given by 1 by s. Now, for the exponential function, that is e to the power minus a t u t, for a greater than 0, you have to put the value of function. So, the function here is e to the power minus a t u t. When we put the value of function in the integration and we solve, we get the output of this particular integration as 1 upon s plus a. Here also you will integrate between 0 to infinity, because the unit step function is 1 only from 0 to infinity. So, you will simply get the Laplace transform of e to the power minus a t u t is nothing but 1 upon s plus a. Now, the third function is unit impulse function. So, you will see the unit impulse function here. So, if you remember the condition for unit impulse function, we discussed that the value, that is minus infinity to infinity delta t dt is nothing but 1, because the area for this particular unit step function would be 1, and this infinity to plus infinity can be replaced by the limits as 0 minus to 0 plus, because for rest of the region the value of delta t would be 0. So, this we already know. So, if you apply this knowledge and you try to find out the value of the Laplace of delta t, because the impulse function is 0 everywhere except at t is equal to 0. So, you will finally get the value of integration as e to the power 0 minus, and the value of this is 1. So, the Laplace of the unit impulse function is 1. Now, next let us see the function f t, that is sin omega t u t. The Laplace transform of sine function can be given as if you integrate between 0 minus to infinity. So, since it is a u t, that is unit step function attached with sin omega t, so it means that instead of having limit 0 minus, you can put limit from 0 to infinity, because for that period only the function will be having the value of sin omega t, otherwise the function value is 0. So, what you can write, that is integration between 0 to infinity sin omega t e to the power minus s t dt. Now, we have one as a exponential expression and another is sinusoidal. To solve it, what we can do, we can convert the sin omega t term in the form of exponential, that is e to the power j omega t minus e to the power minus j omega t upon 2j into e to the power minus s t dt. Now, 1 upon 2j you can take it out because it is constant, and when you club you will get the expression in the form of exponent. So, first is e to the power minus s minus j omega t minus e to the power minus s plus j omega t. Now, we just now calculated the value for expressions, that is if you see e to the power minus 8 t into e to the power minus s t dt, the value was 1 upon s plus a. So, we will use the same. So, what we can simply write, so the Laplace of this will become 1 upon 2j 1 upon s minus j omega minus 1 upon s plus j omega. Now, if you simplify this expression, the final value which you will get is omega upon s square plus omega square. So, for the function sin omega t, the Laplace transform would be omega upon s square plus omega square. Similarly, if you put cos omega t instead of sin omega t, you will get expression as s upon s square plus omega square. So, this you can verify offline by solving the integration and putting up the value of cos omega t, the expression will change in that case and you will solve. Now, let us see few of the properties of Laplace transform. The properties of these Laplace transform help us to obtain the pairs without directly using the integration method. So, that is the initial expression which we started with was f Laplace of f t is nothing but f s, which is nothing but integration between 0 minus to infinity f t e to the power minus s t dt. So, we will use various properties to directly find out the value of Laplace transform rather than going with the standard procedure of the integration of the function. So, let us see what are those properties. First is linearity. So, linearity means if f1s and f2s are the Laplace transform of f1t and f2t. So, what we can say that Laplace of a1 f1t plus a2 f2t will be nothing but a1 f1s plus a2 f2s, where a1 and a2 are the constant. So, this will be showing the linearity property of the Laplace transform. So, next is scaling. So, if fs is the Laplace transform of ft, then for Laplace of f of at we need to find out. So, let us solve it so that we can understand what is the value of the Laplace of f of at. So, based on the standard definition of Laplace transform, we can say that the integration between 0 to infinity f of at e to the power minus st dt. So, a is constant and a is greater than 0. Let us assume x is a variable which is equal to at. So, dx will be a dt. So, if you put the value of x, so you replace the value of t by putting the value of x. So, f of at will become fx, then e to the power minus s t will become x by a, and then dx will become a, then dt will become dx by a. So, 1 by a will come outside the integration because it is a constant term. So, Laplace of f of at is equal to integration 1 by a into integration of 0 to infinity fx e to the power minus x s by a dx. Now, if you compare these two equations, because this is the standard definition of your Laplace transform. So, that means that you are simply replacing s by a. If you replace s by a, both will be same. So, what you can say that when we compare, the definition of Laplace transform shows that s is this, the standard definition, and you replace simply s by a, while you change the dummy variable t with x. So, when you compare both of them, you can simply say that Laplace of f of at is nothing but 1 by a into f of s by a. So, this is what you got. 1 by a is anyway constant, so you can take it out. So, now if you compare these two, the only difference is that you are simply replacing s by a. So, with this simple comparison by visualizing both of the equations, you can say that Laplace of f of at is nothing but 1 upon a f of s by a. So, if you use this particular the condition, you can say that since you know that the Laplace of sin omega t is omega upon omega square plus s square, then for Laplace of sin of 2 omega t can be given as, by using this equation you can write simply as 1 by 2 omega upon, instead of s you will write s by a is 2 here. So, s by 2 square plus omega square. So, when you simplify, you will get the value of sin Laplace of sin of 2 omega t is nothing but 2 omega upon s square plus 4 omega square. So, this is what we call as scaling. Now, let us see another property of the Laplace transform, that is time shift. So, if fs is the Laplace transform of ft, then Laplace of f of t minus a into unit step function u t minus a will be given by you can simply use the standard definition of Laplace transform. So, you will integrate between 0 to infinity f of t minus a u t minus a e to the power minus s t dt, where a is greater than 0. Now, u t minus a is 0 for t less than a, and u t minus a is equal to 1 for t greater than a. So, you will use this property, then your integration will become integration between a to infinity f of t minus a e to the power minus s t dt. Now, let us assume that x is another variable which is equal to t minus a, then your dx will become dt and t will be x plus a. So, as t tends to a, x will tends to 0, and as t tends to infinity, x will also tend to infinity. So, by using these conditions, you can simply say that the updated integration would be 0 to infinity f x e to the power minus x x plus a. So, t is simply replaced by x plus a, and instead of dt we are saying the expression in form of dx. Now, if you see this expression, e to the power minus s a is constant. So, you can take this out. What we left is 0 to infinity f x e to the power minus s x dx, which is nothing but the Laplace transform of a function f t. So, if you compare with the standard definition, you can simply say that this is the Laplace transform of f x. So, you will simply say that the Laplace transform of this is f s. So, finally, what you got is the Laplace of function f t minus a u t minus a is nothing but e to the power minus a s f s. So, this is called as a time shift. So, that means that a function is delayed in time by a, the result in s domain is multiplying the Laplace transform of the function without a delay by e to the power minus a s. So, in this, if you have a time delay in function, you will simply multiply the Laplace transform by e to the power minus a s, and then you will get the Laplace transform of a function which is delayed in time by some constant value a. So, this particular property is called time delay or time shift property of the Laplace transform. So, with this, let us take the example of the cos omega t Laplace. You know that we discussed that the Laplace of cos omega t is s upon s square plus omega square. Now, if you are asked to find out the value of cos of omega t minus a, what you need to do? You have to simply multiply the f s, that is the Laplace transform of cos omega t, by e to the power minus a s. So, without going into the complete integration, you can simply use this time shift property and find out the value of cos of omega t minus a. So, now let us close our session at this point of time. We will continue our discussion in the next class, where we will discuss few more properties of the Laplace transform. Thank you.